whatever's available, and we try to apply the same hammer to every problem we come across. Monitoring during treatment is very limited if it's conducted at all. I'd say the most thing that I've seen is monitoring a pH and visual turbidity, discoloration and so forth. Once we've alleviated the problem, we typically don't go back until there's another problem. So understanding what happened, understanding what worked, trying to build a case or some more information on that well typically doesn't occur, unfortunately. So as mentioned, with regards to fouling, it's a little bit of everything. It could be a well on fire like this one here, receives heavily mineralized water from one zone of recharge. It would be on your right. That would be the eastern side of the valley. It's Wasatch Mountains in mid-Utah. The left side is the Jordan River influence, a very active alluvial setting, a lot of organics, resultant with the biology. And I've never seen and still haven't seen a well divided just like this, and how you can see where it receives recharge throughout the year. So I always enjoy this one. Particular well was cleaned, and the cleaning didn't work. They had brushed it, they had swabbed it and baled it, got a lot of material out, but failed to really get the perforations. And the louvers there you can see are fairly occluded with mineral scale buildup. They got the easy stuff, the low-hanging fruit, but now it's time to move in with chemistry and dissolve that and open up so we can get deeper into the well setting. Revisiting iron bacteria from earlier, the signs were always here in this well 18 months prior. Total iron was creeping up. If they had looked for iron bacteria, it was present in samples, static and active pumping. That was the pump, and this was the screen, the same well system there. Relatively new pump and motor. Not as efficient as it once was.
How to get water in.
Exactly. Fortunately, the contractor ran a video survey before running a surge block down here. Structural activity in central coast of California, kind of a borehole collapse and a pinch there. So mineral scale, we see it build up. When I say we see, video surveys, we'll see it in the screen zone and in the casing blanks between the screens right up to the water level. It's direct accumulation and buildup. Typically, there's a biological component that is the anchor mechanism. It's the fly paper, it's the glue that the minerals precipitating out adhere to. Generally, when we see it inside the well, it's already built up in the filter pack. And that's the rub there. That is the harder material. We can't get a brush into that zone. And even when we get chemical, we've got to get chemical through the screening device, through the filter pack, and dispersed in that area there. The most common we see, as we mentioned earlier, iron oxide, followed by calcium carbonate, followed significantly lower by calcium sulfate. The good thing is typically when we do find sulfate, it's mixed with carbonates. So it's, if we can break one down, we can typically break the other down, or at least mobilize it a little easier. Biological, as I mentioned, we're chasing pathogens or indicators of pathogens, but we've got a lot of other issues that are derived from bacterial fouling, not just water quality. So we've got taste, odor, discoloration, such as this sample jar right there. I think the colloidal material is a little washed out, but it kind of looked like marmalade. A little thinner, a little more mobile than marmalade, but not something you want to be drinking. It enhances the mineral scale buildup. The American Water Works Association did a study several years back, and they attribute 80% of the well fouling to biology. That's either direct or indirect. And it's that fly paper, it's that glue that a lot of the precipitating minerals build up into. But then we have direct blockage, like you saw that pump. We see it build up on the screen zones. We see it occur in the filter packs. Mechanical fouling, and this is the sleeper out there. Generally, we're addressing it with some of the same methods. The surge block, the jetting, and so forth helps to mobilize that material. Over pumping, it flushes it out. But if we see a well that's off from original production, or it's declining in efficiency with an increased amount of drawdown, very erratic turbidity. For example, we get this sample one day, pump a week without anything, and then we get another chocolate milk type sample. Characteristic of a lot of alluvial aquifers with fine sediment infiltration. Not uncommon to see a well have a mechanical fouling at the 10-year and then 15-year marks, depending on how actively pumped that well system is. Also, if the construction, if it was mud rotary and we had a lost circulation event or some type of delay in materials and the well stayed open for a longer period, or some type of disruption in the normal operation of the drilling, it's not uncommon to see drilling fluids remaining downhole, kind of as a headache there. Here's some pictures of poor development. These two here, we've got the louvers and we've got the screens. The core construction, the barrel of that is clean, so we've been able to search it out, but the actual flow zones is heavily impacted there with drilling fluids. It's a little washed out there. The image to the left is what they call the glass phase transition, when you have polymer in a well system and it is oxidized and it's become very solid, kind of like old Scotch tape. That's what you see. You see that microscopically. If you catch it in the light, you'll see it in your hand. You don't even need to magnify it. So treatment process, and this is an ideal situation. And what I advocate is the more you know going in, the better you can handle the surprises that inevitably are going to occur on the job site. So can we identify the problem? Is it biological? Is it chemical? Is it mechanical? Is it straight current coming from a local industrial concern? So take the time to understand that. Look at the impact. So is that impact an aesthetic issue? Or is the efficiency of our well system pretty significantly impacted? Use that information as well as what we know and what we're capable of to develop a plan. Let's make sure we've got the right materials. If we need a pump, let's make sure it's in good working order and it can mobilize sufficient volumes to make a difference. If we've got a brush or a surge block, again, are they in good working order? Are they clean and ready to be used? If we need chemicals, what's the lead time to get them in? What are possible interactions with the well, with the other chemicals on site? What's the health and safety plan for our crew? What if it gets loose at the well site? Do we have impacts on the environment? We understand all this beforehand, so when the surprises or the accidents or the spills occur on site, we can respond a lot more effectively. Follow the plan as best as possible. Monitor, monitor, monitor. What's going on in that process? Is there something visual? Is there a chemical parameter we need to evaluate? Keep up to date on that and document if we can. And then post-treatment, once we're done. Did we succeed? Did we fail? What can we do the next time we're at this well? Did something work here that might work in another well system? Advocate physical site inspection. Murphy lives around the well site even when we're not there. So was it struck by lightning? Did it get hit by a drunk driver? Did the person run into it with a mower? Did someone back into it? Did we have an earthquake that occurred? Something that might have shifted off at the wellhead, interrupted the seal, signs of burrowing, anything like that that could give us a further indication of what's going on. And then also let us know another thing that we need to resolve while we're there. Check the electrical and the wiring. Is there evidence of a short? Was something grounded wrong? Has there been a disconnect? Especially in smaller well systems, a lot of people will try and DIY it, and they don't always do it right. In municipal systems, whether it's remote monitoring equipment or the city trying to find another revenue stream, we've seen a lot of material grounded to the well, and now they're inducing a current and pushing the corrosion envelope on that well system. Do we even know it's occurring? So inspect, inspect, inspect. Collect samples if we have to. Water sample, as we talked about in the last session, catch a static, catch an active pump, and look at the differences there. If nothing else, some visual inspection. Let it sit and see what sediment builds up there. If you've got sand grains in that clear active pumping sample, we may have a mechanical issue. If you've got little orange cotton balls developing in the static sample, we may have an iron bacteria issue. So even if we can't get it to a lab, let's monitor how that sample behaves on the windowsill for some insight. Scale samples, they're great, and they're also horrible. In a great sense, they are a specific example of the fouling mechanism occurring at that point in the well. And we can take that material, we can test the chemistry on it, see how it reacts. We can try it with a tool to see what type of physical energy it needs to break apart. On the bad side, it's just specific to that one point. So if it's coming off the pump and we target our whole rehabilitation plan to that, we may miss what's going on in the rest of the well. But it does at least give us some insight. With water chemistry, some of those same parameters we talked about in general. Is it aggressive? Is it scale forming? Do we have solids congestion occurring? Do we have any evidence of physical infilling? We got iron concentrations that we know are a problem in that area. Iron, manganese, calcium, magnesium. Is it corrosive? Is the water potentially aggressive there? We're going to have to honor that and not do any further damage with our cleaning. This information then can give us some insight. For example, if we do have calcium sulfate scale, we're not going to go in with a sulfate chemistry to resolve that. It's too light, they're too similar. If we do have a corrosion potential, we don't want to go in with a highly aggressive hydrochloric acid. Or if that's what we can get, we want to limit our time down hole so we don't aggravate that corrosion condition. On the biology side, there's resident bacteria in the groundwater, and we need to be comfortable with that. So what has happened? Do we have a very large population of 100,000 CFUs or more, or is it pretty minor? And so we can adjust our biological attack, our disinfection, a little bit differently there. What is occurring? Are they increasing rapidly? Are they anaerobic? Is there any specific bacteria that we know are going to be a problem, such as an iron oxidizer? Conduct a pump test. Or if we can't do that, look at the efficiency of that motor. How impacted is the well system? If we're dealing with something that's 80% off of design or original, we got to go in there with multiple methods. We're going to have to really apply some time, energy, and money to resolve that problem. We're trying to wake up the dead. If it's off 15 to 20%, we don't have to be as aggressive. And we know our target's a lot more achievable, i.e. cheaper and faster. If at all possible, run a video survey. They have advanced considerable, the costs have gone down. It still is a luxury, but it gives us eyes-on inspection of the fouling in that well system, as well as the well structural integrity. It helps us identify those pinch outs like we saw before, or the hole in the side of the casing from earlier, that we can then adjust if we've got to do some structural modification, so we're not fishing blind if that's a particular case. If nothing else, let's measure the amount of fill or debris in the bottom of that well system with a tape and see where we are, make sure we get that material out at the end of the project. All this goes into developing that plan. So what's the age of a well? Newer wells, we can be a little more aggressive, the damage is a lot less likely, it's generally more resilient materials. Older well systems, we typically treat with gloves, typically a little more fragile, a little more potential. Also, they're not designed to the same current standards, so we've got to keep that in respect. The degree of impact, like I talked about, if it's 80% off of original, we're going to need to be a lot more aggressive, multiple methods, both chemical and mechanical. But if we're only 10 to 15% off, we don't have to be as heavy-handed. Historical treatment, or the lack of, what worked, what didn't work, what did we chase the last time we were in there. So if previously just went in with airlifting and a disinfection, and we're now back 6 months later, I wouldn't repeat that. Or if we repeat it, have other steps in there to enhance the treatment before we go back to that type of treatment. What's the role of the well? And we talked about this in the last session. If it's the only well that you've got, one, we're going to be a lot more respectful of potential loss or damage there, but we're going to use multiple methods typically. If it's one of a number and we can take it offline, take it out of rotation, and take the time to do it right, that's a luxury, right? Projected lifespan of the well. If the well's already run 60 years and they're due to replace it next year, they don't want to spend a large amount of money or a large amount of time to do it right. And that's going to have to be a consideration. If we're going to be decommissioning it soon, maybe disinfection is as far as we go right now just to get them over the hump there. But if it's going to be a veined well, 25 years, 50 years or longer, we want to take the time to do it right there. And then cost versus benefit with all those things in mind. And that's really the owner's decision. And us in the industry here, we're trying to give them all the information we can so that they can make that decision themselves. I try and put things a lot of times when I'm working through my presentations at home with how would we look at it in our household. And different people, you've got people that stack the dishwasher you know, like they're building furniture for IKEA. You've got others that just throw it in there and say a prayer and hope for the best.
That sounds like my wife.
It is my wife too. She frustrates me. It's a Tetris game. No, sorry. You know, and the same in the sink. You know, you've got the mentality, some people will just take the pot like this, some type of baked spaghetti, they'll throw in some soap, they'll throw in some water, and they'll let it soak. And what do you got 3 or 4 hours later? You got this cold, nasty mess that no one wants to touch. So in a well system, just like the dishes, first let's scrape off the bulk material. Let's get what I call the low-hanging fruit. Scrape that into the disposal and the trash can, let's get that out. Then we've got a lot less material to deal with. And that's going to mean a lot less mechanical and a lot less chemical that's needed to do the cleaning. The soap is the chemical. You know, and if we've got a grease, we want to make sure that it's going to cut that grease. If we've got a harder buildup, then we may need to go in with a bristle brush and really break it down. The best results, 1, we don't wait too long. 2, we get rid of that bulk material. And 3, we apply both the chemistry of the soap, the hot water, so we got fluid flow going in, and then some elbow grease. We got some brushing or some scraping, some surging that's occurring there. And that's, you know, how we get the end results that we want. Maintenance and rehab, redevelopment, you know, it changes. It can be very regional, it can be contractor specific, it can be engineer specific. It really does change, and so I've broken it down into what we see the common issues. Disinfection, you're targeting bacteria. Cleaning, you generally have a mixed problem, and you're going to use mixed resources to address it. Redevelopment is largely for mechanical type fouling or sediment infiltration or remnants from the original well construction. And then structural modification, if we've got to put a liner in, swedge out an area, perforate another area, that we're modifying the core structure of that well system. So disinfection is the most common form of treatment done across the industry worldwide. And it's the cheapest. We repeat it a lot because it's a very ineffective type of situation, but it's also one that's mandated, or it's a regulatory requirement. Anytime we're in that well, we're going to disinfect. As I mentioned, it's often repeated. Generally, it's an oxidizer. Most often, it's sodium hypochlorite, followed by calcium hypochlorite. You do have peroxide used in some parts of the country, and then also isocyanurates. It's a newer version of chlorine, which we'll talk about in a little bit. It's probably the most method that we assume we know the most of, but it largely surprises a lot of people. It's also one of the most dangerous that we utilize, and I think, again, that surprises a lot of people. Acid-based cleaning, we're trying to break down mineral scale. There's a lot of people that will misspeak and say, oh, we're going to burn out the bacteria. That's not what we're trying to do with acids. We're trying to break those mineral assemblages that the bacteria are hiding in or have been part of the buildup. So we're trying to break down the calcium or the iron or the manganese. We're generally operating in an acidic pH range, so less than 3. And so there's a whole host of health and safety concerns operating at that aggressive level. As we're breaking down that scale, there's always going to be some off-gassing. You'll have some bubbling. It can be very violent. It can be very slow, depending on the reaction. You also have some heat generation. And the other thing, which we talked about earlier, total dissolved solids and conductivity will spike considerably. That's chemical congestion that's occurring. And that's the material that we've broken down and the material we want to evacuate from the well setting. So there's a variety. There are acids in powdered form, in liquid form. There's very quick reacting, very slow reacting, different core chemistries, and I'll touch on those. Different use rates, different mixing rates. Monitor the evacuation. At a minimum, we want to monitor the pH, but also look at that total dissolved solids and conductivity, because we added in a chemical agent. We broke down the chemical structure there, so we want to make sure that we flush all that material out, not leaving anything behind. And then we want to look at how we neutralize and dispose of it. It's best to neutralize it, so bring it back to a neutral pH of 7 or so at the surface. And the core reason there, we just spent all this time, energy, and money to dissolve that material down to it. We don't want to neutralize it right in there. We don't want to leave those building blocks for the next problem. And this is true both in acid cleanings as well as chlorine neutralization. We want to pull that material out, take care of it at the surface, dispose of it as we're supposed to regulatory-wise, and move it away from the well environment. Development during new well construction, what we're trying to do is reset that well to a good standard flow, remove all the disrupted materials, the mixing, the cutting, the sediments, the mud that we introduced. We want to flush all that out to have a good stable flow pattern. Now, as a well is operated, especially if it's an alluvial aquifer system, fine silts and clays will, over time, mobilize to the borehole. Generally, they're built up in the lower extension of the well, including filter pack, or if it's open hole construction at the bottom. So we want to pull that material out. In environmental related wells, so monitoring wells, pump and treat, and so forth, their development is typically rushed. And so we see a lot of those wells continually plagued by that. Because some of the changes in the industry over the last 4 to 5 years, development has been rushed. And so generally it's kind of a hangover that occurs in a lot of well systems. This is another one of those wells that was cleaned. And you can see the rods of the wire wrap screen there. So the swabbing was effective at cleaning that bore, that core barrel of the well system. Got a lot of material out, high turbidity, stink, a lot of material out of that well system. Flushed it. Did see some improvement in flow, but they weren't getting the significant improvement they wanted. Went down to the video camera and we could see that we did clean the rods off, but we didn't get into the flowing areas there. And there's a little bit of improvement, but we certainly can't see any filter pack. And there's a lot of material that remains, including those screens, that's going to impede flow and efficiency. Chemicals, it just comes off as distasteful for a lot of our customers. Well, I don't want to put anything down the well. And then the next thing is, well, they're all the same. They think that about their dish soap, they think that about their laundry soap, or when they go to the car wash. But it's not true. We apply different chemicals for different reasons. We learned in the last session there's a host of different problems, and so chemicals allow us different tools to address those different problems. As I mentioned, chlorine is the most common chemistry used, followed with chlorine enhancers that are used to maximize the disinfection effort. Acid solutions come in second to those, to that category there as most commonly used. Polymers, especially in the last 20 years, and the goal there is to enhance the activity of either the acid or the chlorine in the cleaning process, allowing us to use less of both of those. Surfactants, again, right in there with polymers, designed to improve the cleaning efficiency of those chemistries. Phosphates, a little older, but still used for a lot of development efforts in parts of the world. Mud and clay dispersants over the last 10 years, as we've moved away from phosphates, those have moved to the forefront for development and redevelopment. Caustic solutions, maybe 1 or 2 rehab jobs a year that we look at this being an option. And most of the time they are an environmentally fouled well or an environmental well where you've got just an abundance of organic material or an organic contaminant. And so we go in with a caustic to aid in that. And then we've got the exotics, and this is your shape charges, your gas injection, your heated acids, your dry ice, and so forth. And people will come to me, and it's kind of like witching. If it works for you at that one spot, that's great. I believe more in witching than I do in putting shape charges down a well system. But it had to work somewhere, so people will give it a try. But I just wanted to throw that out there as some things used under the chemistry umbrella there. So chlorine, we use it for disinfection. That's where it sees its most use. We utilize it in development to break down any polymers that we may have introduced into the muds, so then development is a lot more effective. And then we use it in decon. So if we've got a well that's been inundated by flood waters, or if we're just moving well sites, we're going to use chlorine to disinfect and decontaminate and reduce influence there. It comes in liquid, granular, and tablet. It also does come in gas form. I've never seen the gas intentionally apply to the well site effectively, but more often than not, the liquid and the granular are what we see out at the job sites. Variety of strengths depending on what chemistry and who the supplier is. It can be everywhere from 3 to 15% depending upon the chemical compound. And that is a direct translation to how much you're going to need to get your target concentration. Blending and application vary. Calcium hypochlorite puck or a tablet is going to go into solution a lot slower than a chlorinated isocyanurate tablet or sodium hypochlorite as a liquid. Shelf life and degradation. Your liquid sodium hypochlorite is going to reduce itself by 1 percentage point of strength every month. And if you open the cap and it's exposed to air or sunshine, it's going to degrade at an even faster rate. So when you're utilizing chlorine, you want to make sure it's a relatively fresh manufacture or it is shelf stable like the isocyanurates or the calcium hypochlorite. May need pH adjustment depending on your core water chemistry there at the well site, and I'll talk about that here in a few slides. The safe use and handling. A lot of contractors, consultants as well, think that the big scare with chlorine is they're going to bleach their jeans. And I get it, jeans aren't cheap anymore. Chlorine can off-gas and kill very effectively. And sadly, as a water industry, we've got to learn this lesson every few years. It might occur in a vault, in a sewer system, in a larger utility, or at a well site out in a rural setting, but we usually have 1 or 2 individuals die every few years because of chlorine gas generation. It is very evident. You see the green cloud, but typically by the time you see it, you're already suffering the consequences of it. So the 3 main categories we see of chlorine that's used in the well industry: sodium hypochlorite or liquid bleach. Comes between 4 and 15%. Try and get, if this is the chlorine you're utilizing, make sure it doesn't have fresh mountain scent or a lemon or a wash additive. That will do you no good. Even if the customer likes the lemon fresh scent in their well water, that additive is no good for our well. Buffered for safety. So if you grab whether it's the Clorox from Walmart, for the local grocery store, or even from a commercial, it's typically going to be at a pH of 9 to 10.5. And they do that for transportation. So it's buffered for safety, lowering the potential for gas generation. So if it gets knocked over in transit or punctured in the supermarket and spills on the floor, it's less likely to create the gas and kill people around it. And that's great, especially we've got to transport it to the job site, we've got to handle it. But we also understand that's reducing the effectiveness of the biocidal component that we want, so we may have to adjust that. Calcium hypochlorite, very shelf stable. It's not uncommon to see people drop the granules or the puck into the well system, let it filter to the bottom. If you've got a calcium-rich water or a hard water, it's going to be very slow to dissolve, if it dissolves. Furthermore, as it dissolves, it's going to be contributing additional calcium to that water chemistry. So you may have to make sure you dissolve it at the surface before you add it into the well. Make sure you're not contributing to scale formation downhole. It is typically stronger, 60 to 99%. It does degrade, but it's a lot slower degradation. And the one thing that I've noticed just from a use and handling is, even though it is shelf stable for a couple of years, the older it gets, the harder it is to break apart and go into solution. Chlorinated isocyanurates, if you're familiar with Sterilene or New Well 420 or Well Chlor, those are some products on the market. This is a new, fast dissolving. It's a sodium base, so we're not adding any calcium, but it's a chlorine compound. Very shelf stable. I think it's roughly about 5 years. It's strong, 99%. It goes right into solution. And they're designed specifically for well site applications. So a real good chemistry there, kind of a new chemistry just in the past few years, and no pH adjustment needed. So with chlorine usage, make sure you got a fresh active form. Check the boron date, or if you can't get that information, grab the container with the least amount of dust and the least faded label on there. For disinfection, our target concentration is going to be 50 to 500 parts per million. Typically, we want to keep that around the 200 to 300 range. At 200 to 300, that's sufficient chlorine for some consumption, especially if you've got some iron in the water, and it's enough to kill without over-oxidizing. Once we get above 500 parts per million, we're over-oxidizing and we're causing the biomass to harden up. And so in the end, it can be counterproductive. Now, we do use chlorine in development to break down polymers. In that particular case, we do want to over-oxidize, 1,200 to 1,500 parts per million. The change there is, yes, it's a high amount, but we're only going in for 4 to 6 hours tops at that real high dose. Chlorine does react with a lot of chemistry, so keeping it in the shop or keeping it on the truck, you want it separate from any other chemicals. Also, you want to separate it from metals because it'll start to cause premature rust on metal equipment that hasn't been coated. Off-gassing does occur. Even the granulars will start to off-gas over time. The reaction we talked about. And chlorine it's a chloride. It is an aggressive corrosive agent. So when we're using it downhole, we really want to leave it no more than 24 hours. And then if we're spraying it on equipment prior to going downhole or material we're pulling out of the well, try and stay on the lower dosage range there. We don't want to promote additional corrosion of metal structures. Now I think this slide laughs at the face of all the PowerPoint rules. Everybody can probably see this very clearly. I can't even see it clear from here. But I wanted to illustrate the difference concentrations, and I'm more than happy to share this with you. But we've got our desired chlorine concentration on the far left, and starts at 2,000 and goes all the way down to 50 parts per million. Then just over to the right of that, we've got our calcium hypochlorite in granular or tablet form, roughly a 65% strength. But then in the middle, we've got our sodium hypochlorite, 5% on the left and 12% on the right. So we've got the supermarket strength and then the wholesale strength. And then our isocyanurates, got a change out here, our granular sodium hypochlorite there. And it changes, so if we're using 25.6% to achieve a 2,000 parts per million, we may need 16 gallons to get that. And unfortunately, if you've been in the industry long enough, this is just secondary to you. You know you're going to need a different amount there. But if you're new or you haven't worked with disinfection or on the development side, the higher doses is there, the variance, it changes. It's not an equal across the board depending on what chlorine you're using. Chlorine enhancers. We saw these come onto the market after the total coliform ruling and the total coliform testing came on pretty strong in the early 2000s. And what happened is we were testing for bacteria more than we had ever tested before, and we were getting a lot of failures. So there was a lot of disinfection efforts going on. Not necessarily a lot of cleaning, not necessarily a lot of understanding, but we were just chlorinating a lot of wells. And what we found is, because of those differences I talked about in the last few slides, we needed to adjust the way we were chlorinating. And that's what this next session will be about. But coming out of that was the onset of chlorine enhancers. And generally they provide some measure of secondary cleaning. They also typically have a surfactant that will reach further out into the treatment zone. And then they also can lower the pH, so you're guaranteeing more production of hypochlorous acid, the biocidal agent of chlorine. Generally, you need to know a little more about your water chemistry, your pH, and your total alkalinity, so you're understanding the buffering capability of the water there. They're generally very concentrated, like 1 to 2 gallons per 1,000 gallons of mixed water, so a little goes a long way. And you want to make sure that you don't use too much so that you generate an acid solution or you have too much foaming because of those components in there. So you need to be very careful about the blending. You also want to look for an NSF approved product. The Johnson product, and John stepped out, it's New Well 410, it's called chlorine enhancer. Acids, as I mentioned, we utilize acids to break down mineral scale component. When we're doing that, we need to understand that we can have potential damage to the well structure if it's very aggressive. We also need to understand from job site safety that we could get blowback, especially if there's a lot of carbonates in the well and that CO2 is off-gassing. So it's going to vary. Not all acids are the same. And I've got a slide here in a little bit to show that. If we're just dealing with straight acids from the wholesaler, we want to make sure that we get a certificate of analysis. And what this is that guarantees that you're not adding any additional metals. A lot of the acids that are available are byproducts of an industrial process. For example, hydrochloric acid can come out of the oil field refinery area and a lot of other industrial components. And it's not uncommon if you get hydrochloric acid for it to have heavy metals in there. You don't want to introduce that into a groundwater environment. So we want to make sure we're dealing with a clean acid that's got a higher grade to it. On evacuation, we want to monitor not only pH, but also look at that visual turbidity and conductivity, make sure that we're flushing all the introduced materials out there. Again, another concern with using too much or too little is the neutralization. We want to maintain that solution hot or at a depressed pH while it's downhole, evacuate it as such, containerize it, neutralize it at the surface, so we remove all those dissolved materials. Common acids employed, hydrochloric is the most common across the continent. Sulfamic would be the second most common. It's a powdered acid, very easy to use, used in a lot of residential well systems. Phosphoric is a liquid acid used in a lot of older wells or wells that have stainless steel completion, less vulnerability, less corrosion concerns there. Oxalic is an organic acid, as is hydroxyacetic. Oxalic is used a lot when we've got organic and biologically entrained iron and manganese, because oxalic has an affinity for iron and manganese. Hydroxyacetic is generally like a pre-cleaner for newer well systems where we know they've sat and developed some biological fouling. It has little legs against mineral scale, so it's purely targeting biological issues. Another one of those catch-all slides, and I apologize for that, but I wanted to get the information there, and I'm more than happy to share this. On the right, the green is our hydroxyacetic and our oxalic. And we've got, hydroxyacetic is a clear liquid, oxalic is a white powder. Hydroxyacetic is typically like a 65% activity. Oxalic is at 99%, so a lot more effective. You want to make sure that you dissolve the oxalic and put it into solution before adding it to the well. Both of them are fairly weak against pure scale buildup. So calcium carbonate will consume those acids very quickly, but they're good against biological components. On the flip side, the red, we've got sulfamic, hydrochloric, and phosphoric. Sulfamic is a powder. Typically we max out at about 5% use rate. It is one of the most aggressive acids when it comes to steel. So if you look at pure steel coupons, galvanized metal, low carbon steel, HSLA stainless, sulfamic bath will actively corrode that material faster than any other acids. Even though we use it at a smaller percentage, it's a very strong acid. Hydrochloric, HCl, it's a single bond, very quick acting. A little goes a long way. When you've got that chloride there, it will actively cause corrosion too if you've got exposed metal downhole. 31% active strength at the high end, more commonly available about 20%. So you're going to be using a little more of that compared to your sulfamic or even your phosphoric. Phosphoric is 13.141 pounds per gallon. It's the heaviest heaviest acid here. 75% strength, so very concentrated acid power per volume there. It's typically a food grade, almost pharmaceutical, and so generally it's a lot more expensive. But that 1 gallon is going a lot further than the other acids. Less potential for corrosion attack of metals too. And so we've got different tools here just in the different acids depending on what we're facing and what condition the well is in. Acid enhancers. The first one is corrosion inhibitor. And these can come inhibited from the factory, so from your chemical wholesaler, or these can be additives added in. There are things like rhodine and zinc oxide components that are blended at the manufacturer, or you have enhancers like New Well 310, which provide some reduced corrosion attack or concerns there in the solution. Generally, Unfortunately, they've got a limited lifespan. So, you know, if one works more than 24 hours to limit corrosion, you're on the fortunate side, you're on the lucky side. Generally very concentrated. They're widely used in the industrial side of things, in the oil field, but on the drinking water side, it's very limited because of how aggressive they are. Got to look for an NSF certification before you add it to the metals, to the acids, or if you're going, like I said, with a commercial wholesale place there, they should have an inhibited that's already pre-approved. Dispersants were designed to allow us to use less acid. So historically, if we would have used 10 to 15% acid on its own, adding in a dispersant can let us use 6 to 8%, depending on the fouling mechanism. The goal is you know, when you add an acid into an environment, you're going to have digestion occurring. It's going to break mineral scale apart. But it's also going to start to neutralize on the back end of that reaction. And so the dispersant keeps that material in solution, keeps it from precipitating back out. So your acid is able to then attack and keep attacking metal and mineral structures, but this limits the buildup in there. So when you go to evacuate, they're more likely going to pull that material out. There are also dispersants that have a biological control agent. So if you've got a lot of material such as this right here, this will keep that from reforming, whether you're using mechanical or other chemicals to break this apart. It'll help it from reforming, kind of like the pond scum does in a hot summer day. Generally on dispersants, you're using less than 3% by volume. Typically 1.5–2% is sufficient there. The usage is going to be tailored to the acid, to the amount of bacteria present, and to the likely scale forming. So the more foul the well is, the more mixed fouling agents are present, the more dispersant we'll utilize. Surfactants, I'm going to jump ahead to this slide here. As I mentioned, looking at this cross section, we may see the impact of the well, the fouling and stuff on the inner well, on the screens, and I've showed some pictures like that. But where it begins is that formation interface as the water's entering the borehole and starting to mix and picking up some oxygen with turbulent flow, and your bacteria are spreading out and setting up, establishing colonies. So that's really where we need to get to. But unfortunately, we've got to get through a lot of space in that well and tricky stuff before we can attack that material. So, you know, our brushing, our mechanical pre-treatment within the well core, get that out, then utilize our chemistry. And we can use a surfactant, which reduces the surface tension and allows the chemistry and the energy to propagate more into the filter pack. If you've got a tight formation or if you've got a deep set fracture system, the surfactant is a good additive for just about everything, because it's going to help that reach. And so then when you go to evacuate that material, you're more likely to bring that stuff in. Surfactants are generally very concentrated. If possible, you want to look at a low foam surfactant. You want to look at an NSF approved surfactant. And, you know, high end is about 1 gallon per 1,000. Once you get more than that, it becomes very sudsy, very foamy, and less effective. It's just too concentrated. Phosphates have been used in the industry for a number of years. A lot of states and provinces have outlawed them, but we still see them applied. What happens is the phosphate forms a long chain polymer, and that polymer can be very cumbersome, but it's very effective at pulling silts and clays out. Unfortunately, the more effective it is at pulling that material, the heavier it is and starts to salt out and precipitates within the well system. So when we do see them utilized, we advocate going little bits at a time, no more than 50 pounds mixed with 300 gallons of water. And then limit your time down hole. If you're starting to see some results, go ahead and start to evacuate out. It's better to then add in additional chemistry than chase it with more or leave it in there longer. And always, if you happen to use this, chlorinate after to reduce any fouling potential there. Mud and clay dispersants, the phosphate-free development chemistries came out as an alternative to the phosphates in the last few slides there, where the phosphate polymers are long chain. Your mud and clay dispersants, your phosphate-free, are small, almost like jacks. They're called quat polymers, and they bounce around. They don't bind up, but they prevent the material from binding up. here's a good example. So your typical bentonites and some of your native clays are an aluminum silicate structure. It's a replicating waffle type structure. And when they get a water molecule in there, they swell. And that links up those structures. And that's where they quote unquote get fat. And that's a real good sealing mechanism, bottom of a pond or within a borehole. What we do to cause them to collapse so we can evacuate them out is you've got to pull the water molecule out. And that's very difficult to do in a groundwater well. So what we look at is, like the dispersants that I talked about, they go in and they knock out that water molecule. And in doing so, they cause it to collapse. So then our physical development processes are 10, 20 times more effective at pulling material out. This picture, this highly turbid water here, was a fully developed well. Even the conductivity was back to normal. We went in with a phosphate-free dispersant, New Well 220, worked it through, started to evacuate out, and got even more both native clays and drilling fluids evacuated. Caustics, we've got a couple of reasons we use them around the job site. In some cases, especially environmental related or environmental contaminants, we use them to break apart the buildup that occurs downhole. For example, I've had a coal tar issue or oil sludge that got into a well system. Both of those, whether you use a chlorine or an acid to treat, harden up. And they're not attacking the organic nature of there, so we use caustics to clean that out and break it apart. There's two challenges here. First, caustics rarely used in the industry, so from a health and safety aspect that we understand, they have a whole host of challenges that are very different from acids and very different from chlorine. So if you get caustic spill on your hands or on the job site, you neutralize with a weak acid. If you spray it with water, the problem will spread, the burn will get worse, you'll have more of a cleanup issue. So that's the first response. Very different, very dangerous in that respect. The second is, if we use a caustic and we're operating at a pH of greater than 9, it's most likely that we are going to change the dynamics of that water chemistry. And we may actually cause minerals to precipitate that weren't naturally before. We're able to target one of those fouling mechanisms, like the oil sludge or the coal tar, but we're causing secondary issues. So when we do caustic cleaning, we typically have to come back in with an acid cleaning afterwards for that secondary effect. We also commonly use them around the job site neutralizing chemistries. The challenge here is getting them mixed. If it's a bigger project, you might set an inductor pipe where the material is pulled into solution. Also, you can look at mixing it into a liquid before, so you're not relying on that powder and the slow dissolving process. It's very common to over-treat for neutralizing, and we go from having a hot acid to a very reactive caustic. So when you're using it for neutralization at the surface, mix, periodically check with a strip test where you're at pH-wise. Once you get to about 8, stop. You don't want to push it even further than that. So ideally you want to be right around neutral, 6.5 to 7.5. The exotic treatments I talked about, liquid nitrogen is a means of injecting and creating a percussive wave downhole. And it shoots energy out, but then brings that energy back. The nice thing about nitrogen is it's an inert gas. So it's generally not aggravating the fouling that's already occurring down there from a chemical standpoint. From a biological standpoint, it's good to pre-treat the well with brushing and get the bulk material out before you go through with that gas injection. That way you're not pushing the slime or the iron bacteria into the filter back or into that aquifer interface. Carbon dioxide, whether it's injected as a liquid into the water zone or dropped in as dry ice, it creates a weak carbonic acid. You get a lot of effervescence, a lot of CO2 off-gassing. It can be very good at freezing the well system in the local area, so it does have some biocidal attributes there. Not uncommon for it to overload. I've heard of well systems that remain frozen for upwards of 6 months. The greater concern I have is if you're introducing and altering the alkalinity of that well system, that water chemistry, and you can create calcium carbonate deposition around there. So similar to the caustic treatment, you may have to perform a secondary acidization. Explosives, it works somewhere. In those hard water states, it's not uncommon to have, there's a process called sonar jetting. And what it is it's a shaped charge set down on the line, and it's set off to cause a concussion wave within that well system and shear the scale off. It's a means of mechanical agitation, if the well can handle it. You do want to remove all that bulk, and typically you want to go in with a secondary acid solution so that anything in the filter pack is dissolved, and then you can evacuate that material out. Heated treatments, these were really popular around 2010. They started to drop off. U.S. Corps of Engineers was very big on this. And the idea was they would take an organic acid and a mineral acid, heat it up to 180 degrees Fahrenheit, and inject it into the well. It is true, you get a very clean, shiny casing and screen. The big challenge there is that heat dissipates very quickly into the aquifer system, and it can linger upwards of 6 to 10 months depending on the rock unit. And that will then offset your saturation index, and we'll typically see a very aggressive biological population growth over that time period. So it's very good at cleaning the well core, but it's got some hangovers that come with it. Again, it probably works somewhere, but your typical well system where you don't want to be in there every 6 months, from a customer service standpoint, that's not a good method. So in choosing the right products, we want to make sure we're going to target the problem. Part of that is knowing the problem. We want to make sure that it's NSF approved. So NSF is the National Sanitation Foundation International, and they look at the water chemistry, they look at the products, they want to make sure that there's no residuals left down whole, that there's no counter reactions, and that the material, that the formula is indeed safe. You want to make sure that your chemical and your mechanical methods complement each other, and they're not going to have any detrimental effects to the well or to the environment. And then manageable post-rehabilitation. If you go in too heavy with an acid treatment and it's not dissolving the problem, or it doesn't get consumed, you're going to have a neutralization issue at the end there. So you want to make sure that treatment there is manageable. Give you a brief introduction to the new well products. John, still out. Okay. So they were first developed in the 1960s, and Johnson Screen started in 1904, creating wire wrap screens. Initially started with bronze and then developed from there. So this was an add-on to the service. It was designed primarily for the residential wells, and that is the 1967 groovy design there for the products.
Yes.
They've continued to add, so as challenges came up, for example, the coliform rule, an effective disinfection, they developed the chlorine enhancer. Looked at different acids with different problems identified, new well 120 and the new well 130, depending on the area there. They're designed to minimize damage, and you've got a screen manufacturer that's looking into that chemistry. And so the idea is that they've got to get a really good feel for the metallurgy there. Product line's pretty involved. The 100 to 600, and I'll jump into those a little bit. Your 100, your D-scale right, is a pelletized acid. It's got a pH indicator, and it's good for if you've got a stuck pump or a small residential well that you can't pull the pump out of, you can drop tablets into the well for fast dissolution, and you've got a pH monitoring with the coloration. It is sulfamic acid based. It does have some oxalic acid components too, so it's designed for your harder mineral scale. The 110 is the granular version of that product. 120 is the liquid phosphoric acid. It's a food grade kosher acid, very good for older well systems where you've got a stainless steel component that you don't want to aggravate the corrosion protection there. New well 130 is an NSF approved hydrochloric acid, very quick, very aggressive form. It's very clean. With the NSF approval, you don't have to look for the certificate of analysis. The polymers and enhancers, the new well 220 is for development and then redevelopment of older alluvial well systems to target natural clays and then drilling fluids. The 310 is a biodispersant to improve acid use. It can be used as a standalone cleaner, although I advocate combining it with an acid for additional cleaning power. The 400 is a surfactant to increase the penetration, whether you're using it for acid cleaning or for disinfection. Very useful product there. On the chlorine side, on the disinfection side, New Well 410 is an enhancer, Chlor Boost. It's got the pH adjustment. It has some secondary cleaning and a surfactant all moved in. The New Well 420 is a stabilized chlorinated isocyanurate. It is rapidly goes into solution. It is a replacement to Sterilene, if you're familiar with that product by Design Water Technology that's no longer on the market. Shelf stable, very easy to use, very easy to ship. Little goes a long way. I think for 200 parts per million, you only need 1 pound of product per 500 gallons of water. So very, very efficient there. New Well 500 Chlor Out is a chlorine neutralizer for disposal, depending on your concerns and regulations. It rapidly neutralizes the chlorine. You can't overtreat with it. Does not impact biological oxygen demand. So a good kind of rounding out the full process. I touched on this. So NSF, you want to look at it regardless of the products you're using. Look at it, whether it's drop pipe, motors, chemicals, what have you. This is the stamp of approval that it's safe for a product to be used in the groundwater environment. And what they do is they evaluate a formula or evaluate a product, they test it independently, and then they will do surprise, unannounced investigations of the manufacturing facility. They'll check to make sure that that formula is as it says. They'll look at, let's say, the process for PVC pipe or for pump manufacture and make sure that it is following the codes and everything that they did. And they do that every year. And there's also a paperwork evaluation. Are the supplies and the components that are going in as are supposed to be? For the New Well products, all of them are NSF that are used downhole are NSF certified, and that includes the drop pipe and screens and so forth. And then also the New Well chemistries are PFAS free. That's not a testing that NSF provides, but that is a growing concern both with EPA and Health Canada. I advocate surface blending for small wells, small tank, large wells, large tank. The idea here is put the products into solution. And this gives you an idea to confirm, let's say, pH or conductivity before you add it in. And then when you evacuate it out, did you bring those mechanisms with you? And then can you control neutralization in the tank? And I'd always err on the side of having more tank than needed, so that if you have some surprises or if the reaction does not move as fast as you'd expect, you have that capacity there. Your treatment, your placement, your contact time, your agitation, all that is going to differ by the products you use and the nature of the problem. Typically, I advocate if you can pull the pump and trim the product right into the screen zone, you're going to get the best results. If you can't, you may need to look at bumping up the concentration so that you can flood the borehole and attack the problem wherever it happens to be within the well system. Agitation, whether it's simple chlorination, development, or attacking mineral scale and biomass, agitation always seems to improve. I do recommend agitation as a means of pre-treatment, brushing or swabbing the well and then flushing that material out, and then once we've placed the chemistry in, agitation, whether it's a surge block, pump to tank surging, or cycling the pump, rawhiding the pump to get some surge in fluid levels. Monitor the reaction. I beat this up and I'll continue at a minimum pH, but grab a sample. Look how it's behaving. Are you starting to see some bubbling? Are you seeing an increase in turbidity or an increase in precipitation that's occurring? Your mechanical energy is going to vary by the well age and its integrity and the well design. So if you've got a telescoping design that goes from 12 to 8 to 4, you're going to have to swap out tooling, and you're going to have to pay very close attention to the as-built so you know at what depths to change that out. Typically, I recommend a nylon brush or nylon rubbers on the surge block so that you're not creating any additional reactive surfaces. The splayed cable, the high tensile strength cable, is really good at hard mineral scale deposits, but if it's scraping into the well structure, it can create additional reactive surfaces for corrosion to occur. Pair your chemicals with your mechanical. so you're not causing any secondary or third order effects there. The level of aggression is going to be dependent upon what that problem is and how impacted the well is. So if you've got to go in multiple times because the well is off 80% of the original, plan that in. Some of the common methods: single and double disc surge block, nylon brushes, and I've seen everything from street sweeper to specially designed brushes that have been used downhole. Just like the surge blocks, you want to make sure they're competent and they're clean. Nylon brushes generally don't last that long, so as they age and the bristles are starting to fall apart, go ahead and plan to replace them. A gas injection, whether it's oxygen, nitrogen, or carbon dioxide, try and again do the pre-treatment before you introduce those, so you're not pushing any of that material into the filter pack. Airlifting, I don't advocate their method of containment around the job site, but it's a very good means of flushing out the lower extension of the well. Typically, the samples you get from airlifting aren't the best, but they can give you an idea of the amount of crud that you're pulling out of the well system. Jetting, water and air. There are some in the industry that will advocate going all the way up to 20,000 PSI. You can start to cut concrete at 18 and with water even less. So I'm advocating slowly advance into it. I like to keep it tops at around 1,200 PSI. If the material is that significant, I'd like to use multiple methods instead of just relying on jetting. Isolation tool, a slight metamorphosis or change on a typical surge block allows you to inject the chemistry right into the area you're working. That's going to be more of a deeper well setting, but it's very good at making sure you've got active solutions right in that zone. Post-treatment, neutralization, neutralize at the surface. Full and efficient evacuation, I've talked about this. Deeper well settings, you want to move up throughout the screen zone and make sure it's fully flushed. True on development also. Make sure that you're meeting your local regulations, whether you need to have a permit in place beforehand, if you need to monitor the discharge at a certain level, try to identify that beforehand so you don't get any surprises. Follow-up evaluations, whether it's testing of the neutralized solution or the well itself, always advisable. And then get the well back to active surface. Even if you're flushing the waste periodically throughout the day, once you've done all that work, keep the well active to limit stagnation and concentration of the problems. Beating up on a dead horse here, but that material that we spent all that time and energy, whether it was chemical or mechanical, to break apart, to dissolve, to attack downhole, we want to evacuate that out. On the biology side, it can be buildup and food source for the next generation of bacteria. On the mineral scale side, you're leaving all that concentrated material down there to then create new cementing mechanisms. Pumps, you want to make sure that it's sufficient to move some water. In larger well completions, I beat this up, but you want to make sure that you're capable of evacuating that well several times over in a very fast and efficient manner. Clean the pumps when you're done. Make sure they work before you go out to the job site. And these recommendations come from failures that I've seen. Typically, 75 to 80% of the chemicals introduced in the dissolving are removed in the first 5 well volumes. If you've overtreated or if the problem reaches further out into the formation and we've utilized a surfactant, we may need to go upwards of 10 well volumes. But if you're monitoring, you'll know when you've reached that point there. Monitor the discharge. If it's the side of an opaque tank or if it's collecting a few samples and looking at it, make sure that you're flushing it out at multiple depths. MHOF cone is great. If you can run conductivity or TDS, that's a $50 to $75 meter. It does require a little TLC there, but it's a great way of ensuring that you've evacuated the well system. Visual turbidity, and I use this as another example to advocate for testing. This is a well operated after it had been flooded and inundated with water. Came up as tomato soup and it got gradually better. If they had sent this sample into the health department, it would have been a no-go. Multiple reasons there. But anytime we've got an issue, whether we mechanically clean the well or chemically treated the well or the well was breached, flush the well. Visual turbidity, You know, even the simple mason jar there, held up against an opaque truck or a white sheet of paper, gives you a real good indicator. If you've got that turbidity there, you still got more evacuation. Touched on this earlier, checking the TDS gives us good indication. I don't know why I added another discharge there, I apologize. Some of the neutralization chemistry, and it'll largely vary on what your wholesaler can give to you. Lime, very cheap. You do get a very quick reaction. A lot of heat is generated. It's very easy to overtreat. Soda ash, probably the most commonly used. Comes in a rice or a granular. Goes into solution relatively quick, but you need to keep the water active for it to dissolve. Good pH treatment. You do have off-gassing, so open air on the tank. I do advocate monitoring because you can also kind of overtreat that one as well. Caustic soda, caustic potash there in the liquid form, goes into solution very quickly. Unfortunately, you typically have to buy a larger volume, 15 to 55 gallons of that. Very quick, very effective in neutralization. Big safety concern if it spills or gets on your hands. You know, big challenge there. Post-rehab video, again, it's a luxury, but being able to go back in after we've removed all the scale and the slime, look at the integrity of the well structure. Also, you know, did we remove the material? Was there anything there that we couldn't see before because of blockage that now is going to cause a change in how we operate, or replacement of the pump, or some structural modifications? Post-rehab, at a minimum, we're going to look for coliforms, as that's our regulatory concern, make sure that we didn't introduce or disrupt anything too far. But I do advocate getting some core water chemistry, base water chemistry parameters for a new baseline. And then you can use that information going back, you know, did we reduce hardness? Did we reduce our iron? What are our new levels for monitoring moving forward? Certainly, depending on the well itself, the role it plays, and the size of that well, this is going to come into play there, but strong belief that this is basically ensuring the job you did was right and that you know what to look for moving forward. Some of the key points as we kind of wrap up: do we know what the problem is? Did we select the right stuff? Did we use it correctly? And are we limiting harmful impacts? Using NSF-approved products is a good means of solving a lot of those, but identifying the problem beforehand so that we can select the right product and use it accordingly. On their website, I've got the URL at the top, but you can also just type in Johnson Screens Well Cleaning in Google. They've got this handy-dandy tool that you put in attributes to the well. Total depth, diameter, static water level, materials of construction. And then if you know any of the water chemistry or microbiology, as little or as a lot as you get, it will then give you some guidance as far as cleaning, what they would recommend depending upon their product catalog. In addition to it, all the products from Johnson Screens have a YouTube video. These are condensed down to just, I want to say 8 to 10 minutes, but they cover PPE, health and safety aspects, and when to use certain products. If you just type in Google New Well, you'll get the host of them. I think there's 8 chemical videos and then videos on the drop pipe and screening devices and so forth too. But it's a great for safety minute for the crews before they go out to use the material, make sure they're familiar with all the safety aspects. That's our second module. I'm going to leave my information and John's information up here. Next, we're going to move into the disinfection side, and I'm going to say let's meet back here at 3:40. So that gives us a good 15 minutes there to stretch, make any calls that we need to, take care of the bathroom break and so forth.